When temperatures push past 40 degrees Celsius and the sun beats down on the pavement, it feels like the perfect conditions for maximum solar power. But that intuition is completely backward. Those blistering summer afternoons actually strangle the electrical grid and force solar panels to severely underperform. The physical reality of a solar panel is surprisingly specific. It requires the sun's light to generate electricity, but it actively rejects the sun's heat. Think of it like being handed a desperately needed meal, but you're forced to sit on a sweltering concrete roof at high noon to eat it. You want the food, you don't want the sunburn. We've actually seen this proof of concept for decades. Old solar-powered calculators run flawlessly year after year, using nothing but the dim, cool lighting of a typical office. But out in the real world, massive utility grids operate in brutal conditions. In places like India, the physical surface of a panel baking in the sun easily reaches 55 to 75 degrees Celsius. Here is the problem. These panels are lab-tested and rated for peak efficiency at an ambient cell temperature of just 25 degrees. When they operate 50 degrees above their ideal state, they bleed power. To see exactly how that power escapes, we have to look inside the microscopic architecture of a standard silicon cell. As severe heat saturates the panel, the localized silicon atoms absorb that thermal energy and start vibrating chaotically. Normally, generating electricity requires electrons to move through this silicon grid in a smooth, highly controlled flow. But those thermal vibrations act like a series of physical roadblocks. The electrons collide with the shaking atoms, lose their momentum, and scatter into an atomic-level traffic jam. The sun's heat doesn't actually destroy the electrical energy. It just creates so much internal physical chaos that the panel struggles to push the current through. This animated diagram illustrates how that microscopic traffic jam translates to the grid. It relies on a basic electrical equation. Voltage multiplied by current equals power. In a mild 25-degree climate, the system is balanced. You might have 10 units of voltage and 10 units of current, giving you a maximum expected output of 100 power units. Heat provides extra energy that kicks more electrons loose, which slightly increases the current. But that same thermal chaos makes it much harder for the cell to maintain its electrical pressure, triggering a severe drop in voltage. So a system that should yield 100 units now drops to 84. 16 units evaporate completely, lost purely to thermal inefficiency. Engineers track this metric closely. For every single degree a standard silicone panel rises above that 25-degree baseline, it loses between 0.3 and 0.5% of its total power generation capability. Extreme summer weather acts as an unavoidable mathematical tax. Every degree the thermometer climbs drains power directly off the grid. Modern panel manufacturers know this happens, and advanced designs continuously try to minimize this thermal loss with better materials and cooling techniques. But physics dictates the limit. Since silicon cells are optimized for that 25-degree baseline, high temperatures inevitably degrade their output. No current engineering can bypass the atomic vibration itself, which raises a very obvious question. If extreme heat guarantees a loss in efficiency, why do the hottest, sunniest countries on the planet continue covering their landscapes in millions of these panels? The answer comes down to a harsh calculation. Capturing a slightly reduced amount of power from an infinite zero-cost natural resource is still vastly superior to the alternatives. Engineers treat this thermal drain as an unavoidable cost of doing business, a calculated compromise baked into our global energy strategy. We accept the tax because the math still works in our favor. We can harvest the sun's light as long as we are willing to endure its fire.